Hello, I'm Laura Marshall.
And I'm Melinda Rose, and this is Light Matters for July 3rd, 2013.
On today's show, a new optical fiber puts a twist on data transmission, a telescopic contact lens helps the visually impaired see, fluorescent fingerprinting aims to increase IDs from hidden prints on bullets and knives, and a father and son's team to explain optical cloaking.
If optical fiber was stable enough to transmit donut-shaped laser beams called optical vortices, such transmissions could help overcome the limits of single-mode optical fibers, which are rapidly reaching their limits from today's ever-increasing demand for data-intensive activities like video streaming. BU's Siddharth Ramachandran, USC's Alan Wilner and colleagues demonstrated not only the stability of such beams, called orbital angular momentum beams, in their optical fiber, but also their potential to boost internet bandwidth. Their new strategy, called OAM Mode Division Multiplexing, combines two approaches used today, wavelength division multiplexing and mode mixing. Several colors were packed into each mode of a 4-mode OAM fiber designed by Ramachandran. For each OAM mode, they could transmit 400 gigabits per second in just a single wavelength of light, or 1.6 terabits per second across 10 wavelengths over the length of 1.1 kilometers. They reported in Nature Photonics last year that OAM encoding could be used to send 2.5 terabits per second of data through free space, but that method didn't work when it was tried in a standard optical fiber. The new work was published in Science.
A slim telescopic contact lens that switches between normal and magnifying vision in combination with liquid crystal eyeglasses could provide a relatively unobtrusive way to enhance the sight of patients with age-related macular degeneration, or AMD. Simply correcting the eye's focus with contacts cannot restore the central vision lost from a retina damaged by AMD. Visual aids that magnify incoming light help spread light around to undamaged parts of the retina, but these optical aids use either bulky spectacle-mounted telescopes or microtelescopes that have to be surgically implanted into the patient's eye. The system, developed by UCSD professor Joseph Ford's team, uses tightly fitting mirrored surfaces to make a telescope that has been integrated into a nearly 1 millimeter thick contact lens. The center of the lens provides unmagnified vision, while the ring-shaped telescope at the periphery of the regular contact lens magnifies the view 2.8 times. To switch between the magnified view and normal view, users wear a modified pair of polarizing liquid crystal glasses originally made for viewing 3D televisions. Tests showed that the magnified image quality through the lens was clear and provided a much larger field of view than other magnification approaches, but refinements are necessary before the proof of concept system could be ready for commercial use. The research, funded as part of a larger DARPA project called Soldier-Centric Imaging with Computational Cameras, was published in Optics Express.
A new way of detecting and visualizing fingerprints from crime scenes uses color-changing fluorescent films instead of sticky powders and could lead to higher confidence identifications from latent fingerprints on knives, guns, bullet casings, and other metal surfaces. Currently, only 10% of fingerprints taken from crime scenes are of sufficient quality to be used in court. The new technique, a collaboration between groups in England and France, visualizes fingerprints by exploiting their electrically insulating characteristics. Such electrochromic polymers change from one color to another under an electrical voltage. The technique is highly sensitive, as even tiny amounts of insulating residue, just a few nanometers thick, can prevent polymer deposition on the metal below. As a result, much less fingerprint residue is required than is typical for other techniques. Also, because it focuses on the gaps between the fingerprint deposits, it can be used in combination with existing approaches. The team developed this technique further by incorporating within the film fluorophore molecules that re-emit light of a third color when exposed to electromagnetic radiation, such as ultraviolet rays. Their success in combining the electrochromic and fluorescence approaches provides a significantly wider palette to color their films and two sets of levers in the form of electricity and light to control and tune this coloration to achieve the best possible contrast with the underlying metal surface. The technique worked well on fingerprints in the lab. The next step is to apply it to those under more realistic conditions. The work was presented this week at the Faraday discussion at Durham University.
Well, that's it for this edition of Light Matters, the Photonics Industry's only weekly newscast.
As always, you can write to us with your questions or comments at lightmatters@photonics.com, and we'd especially like to thank our viewers on YouTube for all your positive comments, and we hope you keep spreading the word.
We leave you today with the DIY project by University of Rochester physics professor John Howell and his sons Benjamin and Isaac, who decided to demonstrate simple optical cloaking of large objects. Thanks for watching, and we'll see you next week.
What you can imagine is you have an object back here. That's your background. And then on this side, you have your viewer. Okay, so in this particular case, we have a very long hall. And that allows us to have basically what is, you're looking at something from a very long ray. So there's only a very, very few amount of rays that are allowed to hit that cloak, which means you're basically looking at things like it's at infinity. So what you have are these rays, or light rays, you can imagine, coming off an object, hitting off of this mirror, being reflected off of that mirror, being reflected off of that mirror, coming to this mirror, and then going to a viewer in the distance. So in this region, though, it would appear that nothing is here because of the fact that light just gets guided around that. And that's the basic idea of these cloaking devices.
We made 3 different types. This is just one of them. This is probably the simplest. The other 2, one of them involves lenses and one of them involves the refraction of water to actually make the cloaking effect.